Hello again. I've bought myself a new microphone, so I hope the sound will be somewhat better from now on. So welcome to exercise 7 of section 8 of section 1.6. It's been a while since I've recorded the last exercise, so I've used the time studying this series for cosecant and all that stuff that I had many years ago and never really learned. I didn't study it properly at the time. And then some other stuff that I felt I needed to get to know somewhat better. But I won't tell you about that now. Well, let's see. The square of the cosine satisfies this differential equation. So we need to, let's just get going. So it's -2 cosine z divided by sine to the third squared times v squared. That's oh no. And cosine squared is 1 minus sine squared. Now what was it we should prove? So that's not what I get, is it? Oh, this should be squared. Which I did. Sine is to the second, that's v squared. So if we multiply one v in there, we get this. So well, we'll see. Maybe we'll discover what's the problem there somewhat later. B, this function satisfies this differential equation. They call that v as well. I don't like that. So let's call that double v, w. Oh, that's the same. It has the same derivative. So all we need to do is to, well, then it's important that I get the first one right. Sine to the third, that's sine to the sixth. There we have it. So this should be to the third power, and third power, and third power, and squared. There we go. So all we have to do is to substitute this with v minus v plus 1/3, or how is it? It's better to do it backwards. I'll do it backwards. So let's let's do it this way. I like this better, not knowing the result in advance. So we'll just substitute this. Doesn't that give a double root? To the third, 2/3 and 2/3. Four ninths plus a ninth. 2/27. So time to confer. So it appears that this one and this one should cancel. Most unfortunate. And the constant term agrees, but not the first order term. So there are a few mistakes here. So where can it be? Where can it be? Oh, it should be a minus here. So this, oopsie. That's plus. This should be minus 2/3. So it's 2/3 omega square minus 2/3 omega square, cancel out, and then a 1/9 minus 4/9, that's minus 1/3 times 4, that's minus 4/3 omega. And that's what they've got. No, minus, oh yeah, and it's of course minus here. There we go. Good. That was the next one. The discriminant. You see, we already had that in problem 2, so I prepared that. I looked up this problem and my solution, where I found that the discriminant is g2 to the third minus 27 g3 squared. And I did check these coefficients back in the book. There are answers to the problems back in the back of the book. So I have checked that this is correct. So it's called capital D equals g2 to the third minus 27 g3 squared, wasn't it? Yeah. Oh, we just have to check the form here. It was 4x to the third minus d2 minus d3. So we have actually to have it in the form, in this exact form. I just check once again. Yeah, we have written it in the correct form. So g2 is 4/3, that's 64/27 minus 27 times times g3, that's 64 and 27 squared, that's a lot. That's 49, 28, that's 32, 729, 9 divides it, so it's probably right. You know what, it doesn't matter, it's 27 squared. I just realized that they cancel somewhat. So it's 0, naught, nothing, vanishes. That's because we have the double root, of course. With this double root, the discriminant must vanish. I already said that, so that was totally unnecessary. Now start with the infinite product formula. So that was the guy I already had prepared up here. And this replacement has already been done because it's sign Z I have here. I found it on the net. I don't really remember them well. I've never really worked much with I haven't worked at all with them. Now, we shall take the logarithmic derivative, and we need a new don't like this color very much. Now I hope this is right. If we take the two with opposite sign, we get 1 minus z squared divided by n squared pi squared. I write it like this because then we have good convergence. It converges uniformly on compact sets. Now we need to take the logarithmic derivative. Oops. Oh, let's put a c. Cosecant of z, and then that's 1 divided by z, and 1 divided by, oh, do we have to take that by itself? Seems as if. So we have to take it out again. And up here we have to take 1 divided by this one, derive the derivative of this one. Actually don't like to erase, so let's just write it like this. 1 divided by n pi, and we multiply it down here. There we go. And as it's written, this sum converges uniformly on compact sets. So it's actually the derivative we get. Now, that was what I understood. I like this formula pretty well because I feel I can understand it. It has the right poles at multiply of pi, so that makes sense, but that's actually not sufficient to prove it. which just it makes very good sense to me. But if you square it or take it to the fourth, this to the fourth, then they'll have the right poles at n times pi, at multiply of pi, but they and it converges very, very quickly, but to the wrong function. So though I understand it well, it's not an argument that it holds. That was the logarithmic derivative. What did we have to do? Oops. Here we have it. And the derivative once again. Oh, this is not CST, that's the cotangent. Now I need to find this eraser. We can correct this as well. I ought to know this, but I don't. I think it's 1 divided by sine square, but maybe it's, we'll just do it very, very carefully. So it's cosine divided, that's minus sine squared. And then cosine times this differentiated. So it gives minus 1 divided by and that comes from differentiating this, the limit of the sum, infinite sum up here. And this converges uniformly, absolutely, on on compact sets. So we can just write it like this. And here we have the same thing, that the poles make perfect sense. The poles at multiply of pi. So I feel good about this formula. And I have tested it, actually, that it works. But I have to warn you, if you do it with higher powers, like 4 or 8, they do not agree. And of course the problem must be well, I don't know what the problem is exactly, so let's forget about that. So, what did the problem say? That was the infinite sum for cosecant squared. Now we need to prove this. So now I regret that it was so long ago I made the other exercises, because I'm sure we need to apply the last exercises. So I'll just take a break where I look at the last exercises and then see if one of them can be used for this. So back again after a little break where I took out a cake for my afternoon coffee. So what I thought might be relevant here was the limit of G2 and G3 for exactly the lattice we are investigating, which was in problem 7, so that we were able to see that they satisfied the same differential equation. Oopsie, that was not what I meant. I meant to put it out here, so it's the same differential equation. But I think I have a better idea, and that's to use the definition of the Weierstrass P function. So we are now at E, and that was the definition on page 16, formula 4.1. Now, when we take the limit, the lattice was, now what was it? N pi plus MIT, no, MI, oh yeah, MIT, and then we let t tending to infinity. Then all the lattice points with a large imaginary part will uniformly tend to 0, so they vanish. So we only have the sum for the real values of L contributing n pi and this was for n non-vanishing. So, but we have that here, and we can take this guy out. So we get squared minus this sum and the factor 2 comes from collecting the negative and positive values of n. Oh, now we need this result. Okay. And this is pi squared sixths. Wow! That was lovely. When I started this, I must admit I felt pretty sure that I wouldn't be able to do it. But now I'm beginning to feel much more in tune with the Weierstrass P function. So that's very nice. I really like these exercises, but they are challenging.